Hi everybody, my name is Doug Barr and it's my pleasure to welcome you to the St. Helena Forum's 2023 season of free artistic performances and exchanges of creative and innovative thinking on a variety of humanities-based subjects. As most of you know, the Forum is an educational nonprofit with a mission to inform, entertain, and we hope occasionally inspire. Today, we'll be listening in on a conversation between David Fried and Dr. Morty to his friends, Rosen, discussing how to bring star power to Earth in the form of nuclear fusion. Before I introduce our guest, I'd like to take a couple of minutes, though, to set the stage for our discussion with a short video describing the amazing accomplishments by the scientists and engineers at the National Ignition Facility that led to a milestone fusion breakthrough just a couple of months ago on December 5th, 2022.
The universe, for billions of years, has been lit by the fire of countless stars. In these stellar cauldrons, hydrogen nuclei are fused together to form helium nuclei, releasing energy that lights the heavens. Can we build the technology to harness this awesome energy on Earth? As we approach our planet, that is exactly what's happening today. Far beneath these clouds lies the National Ignition Facility, located at Lawrence Livermore National Laboratory in Livermore, California. This facility has been built to bring star power to Earth. It is the world's largest and highest energy laser system. Containing 192 laser beams, NIF will explore controlled nuclear fusion to ensure global security, enable sustainable clean energy, and advance our understanding of the universe. 85 feet tall, the laser and target area building is the size of 3 football fields. Inside are 2 parallel laser bays, each containing 96 beam lines. In this animation, which is millions of times slower than real time, we will follow the process for creating a miniature star in the target chamber by riding along with some of the laser beams. The process starts by first energizing the laser amplifiers in the 2 laser bays by dumping electrical energy stored in capacitors into flash lamps. They convert the energy to light that is absorbed by the laser glass in the amplifiers. Later, when the laser pulses pass through the glass, they will extract this energy, thereby increasing the laser beam energy. Our trip with the laser beams begins in the master oscillator room, where a very low-energy laser pulse is created. This pulse is only 20 billionths of a second long in duration, which is a beam of light about 20 feet long. It's amplified and then split into 48 laser pulses, which are carried over to the 2 laser bays using fiber optic cables. Here, the 48 pulses are amplified in a preamplifier by a factor of about 10 billion. Then they're split into 192 pulses and sent into the main laser system. As we track 8 of these beams through the facility, you can see the path of the beams highlighted in red. The first amplification occurs in the power amplifier. It has 5 glass slabs that were energized by the powerful flash lamps. Then they travel to the main laser cavity that directs the laser light back and forth 4 times through 11 sets of laser amplifier glass in the main amplifier system. This gives the laser beams another boost of energy. During this time, optical components ensure that the beams maintain their required pulse shape, quality, and spatial uniformity. On the final pass through the optical system, the laser light is allowed to exit and travel back through the beam lines and up to the power amplifier once more to pick up even more energy before heading down the long stretch to the switchyard. In total, the energy of the laser beams is increased a quadrillion times as they travel more than 1,500 meters from the master oscillator room to the target chamber. In the switchyard, the parallel bundles of beams are rearranged into a conical configuration, That's so they can be focused into the center of the target chamber and onto the target assembly. The assembly holds the spherical fuel pellet containing hydrogen. Here you see the 8 beams split into 2 groups of 4 beams each, one group traveling up and the other traveling down, heading for equidistant entry ports on the target chamber. Finally, the beams pass through the final optics assemblies, which convert the original infrared laser light to ultraviolet. The beams then converge on the 10mm target assembly called a hole-rom, generating a bath of X-rays. This causes the tiny target sphere to implode and ignite in a controlled, self-sustaining fusion reaction. The same process that powers the stars. This will be the start of a new journey that will bring not only discovery and innovation, but a lasting legacy to the future.
Thank you to the physicists in the audience for your patience, and for the rest of us, I hope that video will be useful as we listen to our special guests. Morty Rosen was born and raised in Brooklyn, New York. He received his undergraduate degree in math and physics from the Hebrew University in Jerusalem and his PhD in plasma physics from Princeton. Dr. Rosen's 35-year career at Lawrence Livermore National Laboratory began when he joined John Knuckles' Inertial Confinement Laser Fusion X group, where he specialized in the physics of a laser-heated hole-rom, which is a small, hollow gold cylinder that plays a crucial role in a high-energy density physics experiments, a role I'm sure that Morty will be talking to you more about shortly. Dr. Rosen designed and analyzed several generations of high-energy density physics experiments in the 1980s, and that work served as the technical underpinning of the stewardship program that allowed for the cessation of nuclear testing in the 1990s. Dr. Rosen also designed the first successful laboratory X-ray laser, culminating in a 25-year worldwide quest. Eventually, Dr. Rosen led the X division himself, and during his tenure helped accomplish a series of milestones on the NOVA laser, leading to the approval to build the National Ignition Facility. In the 2000s, he chaired the University of California's Oversight Committee, reviewing the work of LLNL's sister lab, the Los Alamos National Laboratory's extensive physics department. Dr. Rosen then returned to work on the NIF scale holorum physics, which led to more efficient holorums, a key development in allowing ignition to finally be achieved in 2022. Morty has twice won the American Physical Society Award for Excellence in Plasma Physics Research. In addition, he won the American Nuclear Society's Teller Award for his role in establishing the field of high-energy density physics. He also won the Department of Energy's Defense Programs Award of Excellence 7 times. And in perhaps his most important accomplishment, Morty's been married to his kindergarten sweetheart, Rena, for 50 years. In addition to physics, Morty's interests include archaeology, history, word puzzles, and writing articles on biblical scholarship. Well, by now, I'm sure that those of you who are forum regulars will recognize our friend David Fried. Besides being our favorite guest interviewer, Dave's a screenwriter, a novelist, and a former investigative journalist for the Los Angeles Times. Dave was an individual finalist for the Pulitzer Prize's Gold Medal for Public Service, the most prestigious award in American journalism, and he shared a Pulitzer Prize for the newspaper's coverage of the 1992 Rodney King riots. Dave also reported from Saudi Arabia, Kuwait, and Iraq during Operation Desert Storm. He's a frequent contributor to national magazines including Air and Space, Smithsonian, and The Atlantic. He holds a Master of Liberal Arts degree from Harvard University and currently teaches creative writing at the Harvard Extension School. Everybody, please welcome Dr. Morty Rosen and Dave Fried. Hi, Morty. Hi, Dave. Thanks for being with us today at the forum.
Thank you for having me.
Doug, thank you so much. And Morty, thank you very much. It's an absolute honor. And I have to admit, I'm a little bit intimidated. I've spent a fair amount of time. Thank you. I've spent a fair amount of time trying to educate myself as to your world. And I just want to make sure I've got this straight as to what happened on historically on December 5th. The goal was and is to create what is in effect a miniature star in a 10 millimeter target assembly called a hole room. In that chamber is placed a perfectly spherical pellet containing deuterium and tritium. The pellet is then zapped by 192 pellets. I'm sorry, 102 infrared lasers. The sphere ignites and implodes in a controlled, sustained fusion reaction, all of which takes place in 20 billionths of a second. The heat inside the hole room rises to 6 million degrees Fahrenheit. X-rays start ablating the fuel capsule surface and compressing it at 300 kilometers plus a second, which would be, I guess, as I understand it, going from San Francisco to New York in something like 16 seconds. And then in the final stage of the implosion, the fuel core reaches pressures of 300 billion atmospheres and 200 million degrees Fahrenheit, which is 7 times hotter than the center of the sun. And then the nuclei of hydrogen atoms fuse together, creating a microscopic star lasting 100 trillionths of a second. The blink of an eye takes 3 billion times longer than that. But for that infinitesimally small fraction of a second, you've literally created the hottest place in the solar system. So my question in all of that is, who thought of this, and how did it happen? It's incredible.
Well, it was a blink of an eye that happened or started 60 years ago, as they say in Hollywood, an overnight success, 60 years in the making. My boss, the guy who hired me, John Knuckles, thought of this in the early 60s. And it was basically before a laser was even invented. He thought of the notion of providing a remote source of energy to implode a capsule, a small capsule that could be contained, so that one day it would be an energy source in a reactor that would keep going and not blow up. So small enough to be contained. And John is still alive. He's in his 90s. Of course, he's delighted with this result. He hired me in the early 70s, mid 70s. And we've been trying ever since, with an increasing size of lasers, an increasing series of lasers that can then implode larger and larger capsules, even though the one we've imploded on December 5th was only 2 millimeters in diameter. That's the largest we've ever tried, because that fits with the energy of that National Ignition Facility, this 192 beam laser. Yeah, it's crazy to think of it. And what's crazier is you have to take this, if you think of it, if you blew it up, you have to squeeze a basketball down to the size of a little green pea, perfectly symmetric. That's the craziest part. And I see you shaking your head as how amazing and ridiculous that is. And I have given talks where I've seen senior folks in my field shake their head exactly the way you just did. And it's A, in disbelief, B, in pity that I would believe that such a thing could actually happen, and that I'm wasting my life on this. And December 5th was such a joy that it can happen. I don't know if that answered your question.
No, I think you have. So just backing up a little bit to
Sure.
the origins of this very ambitious project. Was the intention back then to create ultimately an alternative energy source that would essentially ultimately replace the use of fossil fuels?
Yeah, absolutely. It was a way to create energy with fusion, which is Mother Nature's choice of energy. All stars and our sun are operating on fusion. I was thinking, John is over 90, which means when he was born, no one in the world knew how our sun worked. It took in the late 30s, Hans Bethe figured it out and won a Nobel Prize for it. So John Knuckles wanted to take this energy source. The fuel can be derived from seawater. 1 part in 5,000 of seawater is this deuterium. Tritium would have to be remade because it decays with a 12-year half-life. But almost every country in the world has access to seawater. The fuel is essentially limitless, and if it could happen, it would be a terrific energy source, independent of the notion of carbon free. You know, in the 60s, there was no wokeness about carbon free, the need for carbon free. But this is a bonus that has really excited everyone's imagination. I meet random people since December 5th of all walks of life. They all say the same thing. They want to thank me, but they feel like it's not their place to thank me. They say, I want to thank you in the name of all humanity. How am I supposed to respond to that?
Just say thank you, I suppose.
I say thank you, and I do want to agree. I agreed to do this interview because I don't usually do interviews, but I do want to put a sense of reality that this is not happening tomorrow.
Right, and we'll get to that in a little. We'll get to that in a little bit. I do want. Can you take us on December 5th? First, I guess I should back up. What was so historic about December 5th? What happened on December 5th that was so noteworthy?
For the first time in the history of fusion research, and I want to add, the huge fraction of fusion research is something that I was trained in graduate school called magnetic fusion, in which a magnetic bottle, sort of donut shaped, holds a hot gas, a hot plasma, holds this hydrogen, keeps it together, heats it by various ways. That's been the main line, but I switched from that magnetic fusion to laser fusion right out of graduate school. And in laser fusion, we implode these targets, as you said, and have it much denser and essentially not confined. We call it inertial confinement, but that just means it takes time for anything to explode and move. And while it's exploding, it's fusing. I've forgotten the question. What happened on December 5th? Yeah, right. So for the first time for all of this fusion research, a scientific break even happened. That is, more energy went in to creating and heating this plasma. More fusion energy was produced than the energy that went in our case, the laser energy that went in to create this implosion and this heating. And it's never happened before. So after 60 years of thousands and thousands of people working decades, this actually happened. And it opens the floodgates. It gives people confidence that we could and should move on towards making or starting to make progress towards a reactor. So it's quite historic by all means.
You have a whole room. You have the chamber. Just for perspective purposes, sure. Can we take a look at what you've got there?
Okay, let's see if it can be seen. I don't know if it's.
I mean, it is tiny.
It's tiny. It's about a centimeter. Like you said in your introduction, it's about a centimeter long. The lasers don't hit that pellet in the center. It actually hits the walls. It heats them up. It makes a 3 million Kelvin. You shook me with the 6 million degree Fahrenheit, but who's counting? 3 million degree scientists talking Kelvin. 3 million degree oven filled with X-rays that heat the outside of that pellet. And what's really amazing is those little laser beams coming through come from 3 football fields worth of lasers. That's one of the most amazing things. They all fit in those little holes on the top and bottom. Heat this up to 3 million degrees. Heat up the outside of the pellet. They expand outwards, just like a rocket. Exhaust comes one way, the payload goes the other. This entire rocket is expanding the exhaust outwards. All the payload goes inwards into the mother of all collisions at the center. It's a super head-on collision if it's round, if it's symmetric. That takes all that energy moving at that incredible speed that you talked about. And it's a horrible thing to think of a head-on collision of moving at that speed, but that's what it takes to heat up the fuel in the center and make it hot and make it fuse. and self-sustained. Part of the fusion process is helium, and that helium stops within the fuel, heats it up more, and it's a runaway. That's what we call ignition. It gets hot, makes it easier to fuse, gets it even hotter, and it runs away. And that's what it takes to put out more energy than the laser put in.
So this is going to be perhaps a somewhat silly question with a serious basis. I understand that, in the process of experimentation and then reevaluation and the whole process of assessing results and trying to improve upon those results, it's a laborious, um, very very defined process. But what is it like? I mean, let's say prior to December 5th, when you there were laser shots that didn't quite achieve what occurred
Right.
in December. What happens in the aftermath of that? Do you guys sit around in a smoke-filled room and kind of, pontificate on where we went wrong and what can be improved? I mean, I know that I know there are many, moving parts, many people involved. But can you walk us through what goes on after an experiment, after a laser shot? How do you improve upon that previous effort?
Yeah. Thank you. That's a great question. And for NIF, I'll just take a step back. For the entire history that I've been involved in with these series of lasers, we we learn from those experiments. We don't call them failures, and they're not if you learn from them, and that's how science works. Uh, and we started out, in the 70s with the wrong wavelength, the wrong color laser. It was not appropriate. It was making hot electrons, which went into this capsule before the implosion and stopped the implosion. For example, we had to change the laser frequency, and so on. As we moved along, the previous laser to the NIF was Nova. It was 60 times smaller in energy. But we did, and then when I was in charge of the theory and design, I had an experimental colleague in charge of experiments. We were responsible for about 13 milestones on the Nova laser, about implosions, about what temperature this hot oven, this whole round got to, etc. If we could check mark the 13 or about a dozen milestones, that was the minimum requirement to make the case for the National Ignition Facility. Long story about getting it approved, but here we had the National Ignition Facility in 13 years ago, 2009, almost to the date. December 4th or 5th, 2009 was our first real triad implosion. Again, at a larger scale by a lot from Nova. It failed. It failed by a lot. It took us quite a number of years to figure out why, in fact. So after every shot, there's exactly what you said. There's a meeting. We try to figure out what went wrong. It's not easy. It takes a lot more calculations. The designs are done with huge computer simulations that take time and have flaws themselves. And we just keep changing things. We changed every single aspect of that December 4th, 2009 target. Every single aspect of that target was changed to get to December 4th, 5th, 2022. We changed the pulse shape, how the laser delivers the energy in time. We changed the material that the outside of that target is made of, from plastic to high density carbon. We changed the HORAM size, the oven size. We changed the material the HORAM was made out of. Every aspect you can think of, we changed. But perseverance and steady progress, and a tremendous workforce of brilliant and dedicated people from all aspects: the laser, the target, the experiments, the design. It's been an incredible journey.
So given the long-term nature of the process, and
Right.
given the the challenges that that you faced and will continue to face. What was the thing that sold Congress with the idea that they would fund this facility? What was there some sort of I sort of envision like a bunch of scientists from Livermore going to Washington and basically sitting down and essentially trying to sell them a car.
Yeah.
What was the thing that got them to buy the car?
Okay. Yeah. So I don't know how Congress buys cars, but they required us to go through, again, this is in the 90s, to go through this technical contract of the NOVA experiments and those milestones. Every 3 months, we had to appear before a committee of scientists, not from the lab, a very distinguished committee, and show them our progress. And there was only a downside to each meeting. If we failed, the story would be over. We had to show progress and the milestones on every meeting, and every 3 months. It was incredibly intense. So that was required, and that's what we did. And then it was passed on from them to the National Academy of Sciences for another couple of years of approvals. Basically, this was, and I think still is, the biggest science project in the United States. It's a $4 billion project. And Congress doesn't write that check that easily. Having said all that, I think it's true that in retrospect, based on the energy source alone, we probably would not have gotten the approval for the National Ignition Facility. Magnetic fusion is much easier to conceptualize as a reactor, laser fusion less so. So how did NIF get its approval? It took a little something called the end of the Cold War. The Cold War ended. The nation, rightfully so, wanted a peace dividend, which meant we don't need to engage in a crazy arms race anymore, which meant we don't need to, which of course saves money, but testing nuclear weapons costs a lot of money. You dig a big hole, you put a bomb down there, you then put a whole laboratory down there. And when the bomb goes off, the laboratory gets data, sends it up a cable before the laboratory itself explodes. It's very expensive. And so the political imperative was to stop nuclear testing, because what do you need it for? You're not making new bombs. That's okay, but the nation and Congress still agreed we have to keep a deterrent and we have to keep a workforce knowledgeable. And therefore, because of all those decisions, which I think are great decisions, it was decided the nation really needs a big laser that can do this little micro implosion and teach the workforce about that kind of physics without any more nuclear testing. And that is the tipping point for sure that made the nation write the check for the National Ignition Facility. And they weren't and hardly supported, small support for the fusion energy part of the mission. Believe me, everybody I knew working on NIF and the lasers before were working for this energy goal. And basically the nation or the Congress said, get ignition on NIF and come back to us and we'll be happy to talk to you about energy. They needed credibility. On December 5th, we earned that credibility.
Is there still a correlation of responsibilities as far as being, the stewardship of the nuclear stockpile, right, and this pursuit of ignition and fusion? How much of the lab's efforts today are devoted specifically to the nuclear weapons component of the initial responsibilities that the lab was tasked with?
Much more than half, for sure. The lab is definitely very much engaged in the stewardship mission. NIF itself, as a component of the stewardship issue, I'll say roughly 40% of the experiments done on NIF are they're not doing implosions to get ignition in order to make energy. They're doing tiny little experiments on pieces of material to reproduce with a tiny scoop if you took a bomb and took a tiniest scoop out of it, you would get energy densities and conditions that are unavailable on Earth except at the NIF. And you would teach about the material properties of such materials. So that's that fraction that on NIF that is involved in that aspect. Getting ignition itself just raises the game as far as what fidelity the outputs can be towards the stewardship mission. So it's a dual purpose. But now
So,
with ignition, we can really focus much more on beyond ignition to higher gain towards a reactor.
so in my research, I came across something that I thought was very interesting, where the energy yield, there was a fusion shot in August of 2021 where
Right.
the energy yield was 8 times higher than the previous record that was
Right.
set in February of 2021, a few months
Yeah.
earlier. The shot on December 5th produced for the first time signs of what was described as self-sustaining burn fuel wave in the fuel. How were those results? How were those results able to grow so exponentially in such a brief period of time? What was the thing that made it happen?
An excellent question. Where as you get closer and closer to igniting, the process that I described, get hotter, make more fusion, get hotter, is in fact an exponential process. And so moving up that curve will exponentiate your outputs. In brief, the August 2021 shot had a better hole realm. It had as small as those holes are that the lasers went through. We made them smaller. You make them smaller, you lose less of the heat of the oven. You can put more into the capsule. You can make the capsule a little bigger. And we only know now in retrospect that capsule in August 2021 was as perfect as we've ever had. It had no flaws. And that helped because for a year we tried to reproduce that result after August for a year and did not, because every target we tried had flaws in them because it's and defects. It's very hard to make these targets. So what's a mother to do? We can't reproduce this August shot. Well, our laser, it's a team science. Our laser folks picked us up. They gave us 7% more energy. Again, it doesn't sound like a lot, but again, if you're near this cliff, you can move up. They gave us 7% more energy. Our chief designer, Annie Kreitzer, made the right decision, take that extra energy and change the target to be thicker. If you change the target to be thicker, even though it has defects, it reproduced the August shot. Thicker just made the hot center more impervious to the defects that were on the outside of this thicker shell. So that reproduced it and gave us again about the August results. So here's September. We have a target with defects that can reproduce. Why didn't it ignite? Well, it turned out it wasn't as round as it should have been. And once I learned that, I circled December 5th on my calendar because I had full confidence, again, based on experience, Annie can redesign to make a much more spherical implosion. And there was no reason why on December 5th we shouldn't have ignition. And I told people this, they rolled their eyes, but, and there it was. I really had full confidence with a rounder implosion, we could get over the top and put out more energy than put in. And so it was.
So what put us in that what was it like on that?
Yeah.
I know you said you went home, as I remember in our
I
previous
went to sleep because I was at home. It was scheduled for 1 a.m. and I was debating to stay up because remotely you can look at the results immediately. And that was, like many other decisions in my life, a bad decision because I was too excited. I really couldn't sleep that night. So I got up early and looked at the results. And it was very clear that something very significant happened. The temperature, we can measure immediately the temperature of this imploded uh, configuration, and it was 50% hotter than these August and September shots that I described. And I know, and everyone in fusion knows, how the fusion scales with temperature. That meant we more than doubled the yield, which meant we put us over the top. So that was one indication. The second indication right away was this whole realm that I'm talking about that was at 3 million degrees. I noticed in the August shot when the capsule went off, it raised the temperature of the whole realm. Not the laser heating the whole realm, but the capsule going off itself was reheating the whole realm. And there was a little blip on the signal of the X-rays that we measure coming out of these holes. Well, the December 5th shot was a whopper of a reheating signal. It went up to 350 million degrees. It was hotter than the laser ever made it. And I had a theory about that, and I figured, again, we had done it. Still, the neutrons took a few days to actually, the official number, which is the neutrons that come out, took a few days to get at. But I went in the next morning after I saw the results. I shook the hands of Alex Zylstra, the chief experimentalist, and Annie, the chief designer, and said, thank you. I've been waiting 47 years for this. And it went on from there. We waited patiently for another day or so to get a neutron number, and then we knew we had it. It was watching or looking at those results was like, I remember as a kid, well, I was a teenager, looking at Neil Armstrong land on the moon. It had nothing to do with me. It was all about this young team. These are the people who were hired by the people that I hired. There's like my work grandchildren accomplishing this. I was super happy for them, and just amazed that I was watching history. Later on, it occurred to me, oh, this is good. I haven't wasted my whole life. This actually happened. And then it came not so much the negative, but the positive, a deep sense of satisfaction. And you would think maybe euphoria would be the first reaction. It was the last reaction, but thankfully it's lasted 2 months. Here we are 2 months later. I'm still euphoric.
So how was the event commemorated in house? What did you do to, other than handshakes and congratulations? Yeah. How was it marked?
Well, I got a free T-shirt. I worked 50 years on fusion, and all I got was this T-shirt. Everyone got T-shirts, but I think we still haven't officially celebrated. There was a lot of press. A week later was the big announcements in Washington. There was a lot of making sure the numbers were right. It was holiday season, so there were holiday parties going on anyway, and a retirement party. I had 3 parties that week, and I was able to talk to the former director and our present director about all this, and all my colleagues, who were all around the lab, and it was just joyous. I don't know, wall-to-wall joy.
I can only imagine. Yeah. How does a guy from Brooklyn wind up at Lawrence Livermore, as integrally involved in this process as a nuclear physicist? How did you come to be where you are today and who you are today?
Okay. It starts with the National Science Foundation. When I was in high school, they had a program for kids from all over New York to go to Manhattan College, which is in Riverdale. So I took 2 hours in the summer to learn physics and math and computer programming. This is in 1968. And I took a train from the lowest part of Brooklyn to the northernmost part of New York, 2 hours each way. And I loved every minute of it. They taught us special relativity, and it was fascinating. So I got the bug. And then the thing they taught us towards the end and was rushed was Schrodinger's equation and wave functions and things. It was a bridge too far. I could not understand this. But I had to decide on a college major. I said, okay, I'll go study that because I was interested and I didn't understand it. So I had no plans. It was not a career that was mapped out. It was completely a curiosity-driven career path. It's ridiculous, but that's what I did. So I wanted to understand Schrodinger's equation. I became a math major. I was very satisfied learning that. Now comes graduate school. Well, there was no physics course that I took that I was super passionate about. So what am I going to choose? Well, I went to the library. It was a book by Hans Alfvén on astrophysics, which was very well written, though probably the physics in it wasn't right, but doesn't matter. You read a book by a good author, what do? You find another book by that author. Well, right next to it was this book about plasma physics and fusion. And in fact, Hans Alfvén won the Nobel Prize for his work in plasma physics, which is hot gases. Trouble is, that book, just like the Schrödinger equation, had this explanation of why magnetic fusion would work, something called adiabatic invariance. I had no understanding of that at all. Said, okay, I'll go to graduate school and try to understand what the heck that's about. So again, it was just a curiosity-driven, crazy option and choice. Of course, it had the plus that this could save humanity by having fusion. So that's how I went into graduate school. Again, at Princeton was and is a powerhouse for magnetic fusion, and that's what I did a thesis on. But then, looking for a job afterwards, laser fusion really had appeal to me because in magnetic fusion, this donut-shaped machine is the high-tech part. And it's very hard for a theorist to change even a screw in that design. But in laser fusion, the laser is the high-tech part, but it's remote, just like John Knuckles thought of it. It provides energy to a target. It's like the plug in your wall. And a theorist and a target designer can put a new tokamak in front of this target every day. And it's only limited by one's imagination. And that, at least, was not a curiosity-driven decision. That was actually a logically driven decision that worked out because every day for 47 years, I've had the joy of putting new, different targets in front of that laser. And it's been a creative joyride.
Yeah, I was just gonna. Yeah, I mean, you just took the word right out of my mouth. In other words, the joy of the process is it's obviously scientific, but there is creativity associated in what you've done for all these many years.
Yep.
Right. Yeah.
That's exactly right.
So what does the future of fusion look like? I mean, what hurdles will have to be overcome before this all becomes a commercial reality as an alternative energy source, a clean alternative energy source?
Yeah, I think that's the number one question. I think it's the number one issue that listeners are interested in. And I have to say we still have a long road to go. I think people at this press conference for the announcement of this ignition and this gain were quick to point out that the NIF laser is not efficient at all. You're not going to make energy when this laser is very inefficient. NIF was never meant to be a reactor laser. It was a science tool. And it's an old technology, but new technology, the lab has made highly efficient lasers that can rep rates, can shoot 10 times a second. They've shipped them off in Prague. There's a laser like that the lab Livermore built for the Prague laboratory. So you need lasers that are efficient and can shoot this thing 10 times a second. You need targets that are much higher gain, and I think on NIF we can continue to study what kind of gains we can get. I'd like to see our gains go up to be about 10 instead of 1.5. I wrote a paper that a lot of folks have read that really shows on NIF you can shoot a gain of 10. On a reactor you will get a gain of 100, which is what you need for a 10% efficient driver. And then you need to have these target reaction chambers that take these neutrons, stop them in material, heat the material so that water going by turns to steam, turns a turbine, makes electricity. And you need to learn how to um, take some of those neutrons and breed tritium, because that's a very expensive part of the fuel. And lastly, you need a target factory that can make millions and millions of these to keep this process going, because you don't want the lights to flicker. You want them to stay on steadily. That's a very tall order, all those things. The nice thing is, as I said, having ignition has opened the floodgates. Even in the past month or so since ignition, we've had at least 2 companies come to Livermore to try to start agreeing to what cooperative research we can do, mostly on the targets, but on anything else as well. So there's a lot of private industry interest. Mostly they're magnetic fusion companies. There's like 30 of them, and they've each got their own creative approaches. And $5 billion of research money is going in from private equity into these companies, which is more than the government is doing. And so how the government decides to proceed and how to collaborate and cooperate with these private companies is an interesting political, sociological question, of which I have no wisdom to impart. It'll be quite interesting to see how that goes.
Well, I'm assuming that a lot of those companies, their incentive is profit motivated, and not to save the world. So
right.
I wonder. I mean, how that works? Do they take a piece of the? If this does ultimately come to fruition in a commercial sense, do they own a piece of the technology? Do they profit from them?
I suppose that's what it'll be, the intellectual property. And if they're really aggressive, they'll build the reactors. But I think it's got a long way to go. But
so
at least now there's interest, more than interest. There's I think, an imperative to proceed.
And so, how much of the work that is still to be done at Livermore and in other labs around the world that are exploring fusion? How much of that effort is predicated on this infusion of corporate money?
Well, I don't think much. I think the government. I don't know. I would hope that Congress hears the voice of the people. I have zero social media footprints. My kids do, and they have circles, and they get from the furthest reaches of their circles the same reaction to all this. That this ignition result of December 5th has given them hope for an energy source that is carbon free. And I think beyond that, to the fact that of the 7 billion people in the world, 5.5 need a lot more energy. And how are they going to get it? And so there's an imperative to put more effort into this. And Livermore is right now leading. We've got a NIF and a facility to increase gains. The French are building pretty much a twin of NIF, but they're building it slower. We started at the same time. So they would be helpful. The Chinese have about a laser about a third or a fifth the size of NIF, but all they have to do is decide and write a check, and you'll see a NIF-like laser coming out of China. And they're doing very, very nice independent research on that. We don't talk to them much, but with the French, we talk a lot. The Russians are building a laser, green light, also size of NIF or larger. We've never seen much real results out of Russia. So the world is certainly waking up to this.
How do you respond to those naysayers out there who say that this is effectively all, if it's not pie in the sky, it is decades down the road before we see any viability in this process, as far as alleviating our need for
Yeah.
fossil fuels?
Well, I would say the imperative is there to try. If if it's decades down the road, it ain't going to be less decades down the road until we start working on it. We have to work on it. I feel like it's a crime not to. And if we don't succeed, at least we tried. We only got one planet. We need to take good care of it. And this may be a way.
So what is next for you as it relates to the exploration of fusion? What are you working on now?
Uh, I'm I've always been much less an implosion capsule guy than I am a whole round 3 million degree oven guy. And part of our success in getting ignition was to make a better whole round. So to use the limited energy of NIF more efficiently. And I think back to this word of creativity and innovation, I feel we've only dipped our toe into the sea of innovation. There's lots of ideas of how to make better whole rounds, different shapes, different materials. And the more we can do that, even with a fixed NIF laser, we can get more gain out of this. But the laser people are promising, again, given money, to actually upgrade NIF and put out more energy as well. So I don't want to say the sky's the limit, but there's a lot of blue sky out there that I feel very energized. We can proceed on to get the gains up to making this whole fusion energy business even more believable. So I'm super
Why
excited.
why this may be a kind of a dumb question, but why then, why not have a laser shot every other week? What precludes the
Yeah.
lab from conducting these experiments on a more frequent basis?
Yeah, well, I mentioned that between that August shot and September a year later, the laser people gave us 7% more energy. Well, lasers always work on the hairy edge of damage. Otherwise, we're wasting it, right? But damage is damage, and damage is costly. And so right now, I think we can only shoot once every 2 or 3 months with the maximum energy of NIF. So we just because the fear of damaging the laser, it's the only laser we got. We don't want to break it, and so upgrading its energy capabilities will be very important. I wish we
Um,
could. I wish we could shoot more often.
is it a fair question to ask when, at least approximately, the next laser shot is scheduled?
Yes, the repeat of December 5th is scheduled in about 10 days. So stay tuned. Buckle up.
Yeah, and so is the intent there to basically confirm the results of the December 5th experiment?
It is, but I think I'm not sure about this. Again, clearly, I'm the grandpa. I'm not involved day to day issues. I think we're going to get a better quality target with less defects. So maybe it'll
Okay.
do even better. But
Okay.
I'm happy with a repeat for now.
So may I ask, how old are you?
71.
71. So a lot of guys your age are off playing golf or doing
Yep.
whatever they do at 71. How long do you intend to keep doing this?
Well, my financial advisor asked me this just yesterday. I don't know the answer. I'd like to do it a couple more years. I'd like to see the gains go up. But life is short, and you never know about health and all those things. I have a house full of books that I haven't read. I'd like to. And the other day, my daughter was giving a reading in a wonderful bookstore in Berkeley for her new book, and I my jaw dropped open when I saw all the books on the shelf that I would like to read. So this is a conflict for me. Um, well, anyway, I hope I can do it a couple more years. It's up to my wife. If COVID really has put a damping on our passion, which is travel. Uh, if COVID really settles down, then maybe earlier because we like to travel.
Well, this has been beyond exciting, and I would concur with those of you, those of your fans who have approached you and have thanked you for essentially, at least being on the ground floor of saving mankind. I wish you much continued success, and I can't wait to see what happens with the results of the next laser shot. It sounds very, very exciting.
Thanks very much, but I really want to make sure I note that it's not me. It's an entire huge team. It takes a village, and it's now the next generation taking over. It's not my job to finish, it's just my job to help it along, and I'm super proud of them. And I've enjoyed talking to you.
Likewise, thank you very much for taking the time. Now I will let you get back to saving mankind.
There you go. Work's never done.
Thank you, Morty.
Okay.
It's been a pleasure.
You're welcome.
Dave, Morty, thank you so much. What an incredibly interesting conversation. And thanks to all of you, too, for being with us today at the forum. To learn more about Lawrence Livermore National Laboratory or the National Ignition Facility, please go to llnl.gov. And to find out more about Dave Freed, visit his website at davidfreed.com. If you enjoyed today's presentation, I promise you it's only the first of many interesting programs to come. To revisit archived presentations, to find more information about the St. Helena Forum, and to stay current on program dates and times, please visit our website, shforum.org. We'll look forward to seeing you again in just a few weeks. And finally, as we say goodbye, we'd like to thank the following people for their generosity in making the St. Helena Forum and its continuing programs possible.